Hello everyone, welcome to the week 11 lecture of this subject AE20 Introduction to CFD. So this week contents are mainly based on basics of turbulence modeling, and we will try to cover some of the basic concepts involved in turbulence modeling, and then we shall see some of the tutorial problems. Along with that, in the today's class, we will also be discussing a marker and cell algorithm, okay, which was previously called as Sola algorithm, in order to solve the Navier-Stokes equations. So this had already been discussed in week 8 content, I guess, but we will also try to see a sample program which involves solving fluid flow inside a lid driven cavity problem, which is like a benchmark problem for validating the fluid solvers. So we'll try to implement the code and just check the results. Okay. Along with this turbulence modeling, we will be also covering that particular content in today's class. Okay. So let us just begin with the turbulence first. So in this week's content, that is week number 11, mainly we saw on a theoretical perspective what are the various turbulence modeling approaches, and then how you get a solution for a turbulent flow. But before that, we have to be quite clear with what is turbulence first. Okay, so we have to kind of qualitatively, define the turbulence, but there is no specific definition of turbulence which kind of exists. Okay, so we try to define turbulence in terms of the features which it exhibits. Okay, we will discuss these features in detail. Okay, so based on these features turbulence is defined. It's like based on the symptoms you try to tell what is the disease. Okay, so similarly, here also based on the symptoms which are called as features, we try to say whether the flow is turbulent or not. Okay, so that is the main way in which we kind of define the turbulence. Okay, and then what we also did was we went on to see some of the statistics involved in turbulent flow. Okay, so mainly there has been no exact governing model or solution which can actually predict the flow features in a turbulent flow. So we always try to decompose the flow into some mean component and then some fluctuating component, and then try to uh, predict what are the statistics of this turbulence. So what is the average of the fluctuating component, the RMS of this fluctuating component, okay, and then the intensity of this fluctuating component. So that mainly comes under the statistics features. Okay, now after that we already have the conservation equations for the Navier-Stokes equation, that is for the fluid flow. What are the modifications which happen for turbulent flow, that also was covered mainly in this week's content. Okay, and when we tried to look at that, we came across a new term mainly which is called as Reynolds stress term. Okay, which mainly comes from the fluctuating component of the flow. Okay, and then once we kind of got into the mathematical formulation, the main big question was how do we solve these equations. Okay, so for that many of the solution algorithms were also discussed in the weekly contents. So mainly we come up with a closure problem wherein like we have say three momentum equations, one continuity equations, and we have like around seven terms which we have to calculate, 7 or 8 terms. So in order to bridge the gap, that is for the extra three terms, we need some equations, right? So to bridge that gap, we come up with the equations for turbulent intensity and then the diffusivity. Okay, so that is mainly called as a closure problem. Okay, so mainly we want to anyhow calculate the features only, that is the statistics we want to calculate of the turbulent flow. So using that say two or three separate equations, we try to only calculate the statistics. Okay, we are not exactly getting the values of say u dash, v dash, w dash and p dash. Okay, so that is the main thing which we have to keep in mind when we are dealing with turbulent flows. Okay, and there are several models. One of the uh, famous or popular model is the Reynolds average Navier-Stokes equations. Okay, so that is the actually the basic model. Okay, from that comes your large eddy simulations, wherein you try to filter out the smaller swirling motions, which I will discuss in the next slides. So what are these things? Okay, so we try to ignore some fluid physics. Okay, and then only concentrate on some fluid physics and then try to simulate that, which are more important for us. Okay, so that is what happens in large eddy simulations, wherein in case of DNS, which stands for direct numerical simulations, we try to solve the exact Navier-Stokes equation, but at a very, very, very small scales. Okay, the smallest scale which is possible, at that particular scale, we try to solve these our normal Navier-Stokes equation only. Okay, so through that, what we kind of get is we can even capture the smallest energy scales. Okay, that is the smallest swirling motions, and in this respect we can calculate the full turbulent features also. So that is made possible through this direct numerical simulations. But as I said, to capture the smallest scales, we need to have a grid which is very, very fine. That is, there are very small elements, small size elements, so you will get large number of elements. Okay, so for example, if your domain is like 1 cross 1, so that along the x-axis the length of 1 needs to be divided into say 1000 cells. Okay, then you have along the y direction also you need to divide it into 1000 cells. So then what you come up with is like around 10 lakh cells, which is very minimal to say, but in reality you get around 10 million cells and all. Okay, so which are computationally very much taxing in nature. Okay, so only in a research field we mainly see DNS being implemented. Okay, so that is one thing which you have to keep in mind. DNS cannot be used everywhere, whereas in most of the industrial applications, I would say um, this LES is used. Okay, LES or say K epsilon is also used because they are not much computationally taxing. Okay, but DNS is the most accurate method which we have till now. Okay, so that is why in most of the research studies wherein they have time and like they have access to good computing facilities, DNS can be used. Okay, so these were the things which we mainly were covered, which were mainly covered in the week 11 contents. Okay, but before dealing with tutorials, okay, I just want to briefly introduce like where did this turbulence come from, like how was it like initially discovered, and say what are the features we tried to concentrate while defining the turbulence. Like I said earlier, we define turbulence using the symptoms, right? if the flow has certain symptoms, then we say it is turbulent. So let us try to discuss that before getting into the problems, so that we can appreciate this turbulence. We will also try to look at various applications where turbulence is required. Okay. Uh, so let us come to the history of this turbulence. So there was a scientist named, okay, Reynolds, okay, from which you kind of get Reynolds number also, okay. So there was a scientist named Osborne Reynolds. He kind of conducted a experiment wherein he considered a small pipe wherein he made some fluid to flow through that pipe, okay, as you can see in this particular figure. So one thing which he like did was he kind of varied the flow rates of the fluid inside the pipe. So when the flow rate was very small, okay, so the also one more thing is that he kind of injected a dye at the center of the flow. Okay, so you can see through this particular instrument that dye is being injected at the center, okay, of this tube. Okay, so what he observed was that when the flow rates were very small, okay, the fluid flow was happening in a very layered fashion. That is, this center layer was not colliding with say top or the bottom layer, and it was going smoothly. So all the layers similarly which are above and below this layer, they were also going in a parallel fashion smoothly. Okay, so this was mainly termed as laminar flow later on. Okay, but when he increased the flow rate, then what he observed is that after some distance, okay, then these dye particles, they instead of going in straight lines, they kind of went in the bottom layers and in the top layers, which you can see in this particular second figure. Okay, so what was happening was that there was a mixing of layers which was happening. Okay, so this is known as diffusive nature. Okay, diffusion means spreading out. Okay, so basically the fluid layers which were in the top were coming to the bottom, and which were in the bottom they were going to the top layer. Okay, so this is known as diffusive nature, and this is number one symptom of a turbulent flow. Okay, so this is was what he observed. Okay, he did not have any idea of this laminar flow and turbulent flow. He was just checking the behavior of flow at that time. Okay, then further when he increased the flow rate, okay, the chaotic motion started more earlier. Okay, that was one thing, and also instead of this simple diffusion, they were the fluid particles were also going back and forth. Now in this particular case, at least they were going in bottom and top, and they were going in the front region. Okay, they were moving forward, but here there was completely some swirling kind of motion which was observed. Okay, so that is also a second most important feature of turbulence, that there are some recirculation regions, there are swirling kind of motions which kind of happen. Okay, so if I have to explain it more clearly, so basically a fluid particle comes and then moves in a rotating fashion. Okay, so this is mainly called as swirling motion, or they are also called as eddies. And this is one of the important symptoms of turbulence. Okay, and these eddies might have different length scale and time scale. By time scale, what we mean is that the time which it takes to kind of dissipate. Okay, so the length scale refers to its say the chord length, or you can say the diameter, or whatever it is. So that corresponds to the length scale. You have also something called as a time scale. Okay, and you have something called as a velocity scale, the mean velocity of the circulation. So these are three main important scales which come in the turbulence. Okay, so as I said, so this is the second features, the swirling nature, apart from the diffusive nature. Okay, So then you also have like this experiment was performed initially by this scientist, okay, Osborne Reynolds. Later on, Stokes kind of popularized this laminar and turbulent flow theory, okay. So what was done next is that this flow rate was kept constant, okay, which was there in laminar flow, but the tube diameter was increased, okay. So then the scientists observed that again this kind of turbulent flow was occurring with the same flow rate, the smaller flow rate, okay. So they came, and then when they also used different fluids, when they used a thicker fluid like a honey, which whose viscosity is very high, okay, then they observed that even with this flow rate, the second flow rate, even then the flow was laminar, it was going in a straight line, okay. So mainly they came up with three parameters to kind of define this. One was mainly, as I said, the flow rate, which is nothing but the velocity, the fluid, okay. Then you have something else also. You have length scale. So for example, here it is diameter of the pipe, okay. Then you also have viscosity. Here I am talking about the kinematic viscosity, okay. So what they observed is that when the flow rate increased and when the diameter increased, turbulence was happening much earlier, okay. I mean, the flow was becoming turbulent, okay. Whereas if we increase this viscosity, highly viscous fluid, they were having very low turbulence, or else they were in laminar region, okay. So they kind of came up with this particular term, which is famously called as the Reynolds number, okay. So higher the velocity and the length scale, you will get turbulent flow easily, and when the viscosity is low at that particular instant, also you'll get a turbulent flow. So what they mainly observed is that when this Reynolds number exceeds some critical Reynolds number, okay, then the flow becomes turbulent in nature. Okay, so that was mainly observed, and this mainly ratio corresponds to the ratio of inertial to viscous force. Okay, so when the inertia of a fluid particle is very high, you can say that the flow becomes diffusive in nature and kind of swirls around. Okay, so those features are found. Apart from that, as I said, high Reynolds number is also one of the feature. If if you have a flow and if you kind of calculate it before actually doing the experiment, that the Reynolds number is going very high, then also you can say that okay, I'll get a turbulent flow, okay. So that is also one of the feature. Apart from that, it was also observed, and in fact you yourself can try it out. I mean, if you can take a bucket and put some water and then manually stir this water, you can see that there are some small large circulation zones which are formed initially, okay. Initially these large circulation zones are formed. Later on, if you just remove the stirring, okay, I mean the whatever force you are putting, this kind of dissipate, okay, this kind of dissipate into smaller recirculation zones, smaller eddies, okay, and finally there is nothing which is left. So what happens is that these larger eddies kind of transfer the energy to smaller eddies, which is lost in terms of thermal energy when the flow again becomes a stagnant or say laminar, okay. So that is also a feature of turbulent flow, that it is dissipative in nature. The energy kind of drops, that is the energy gets transferred in terms of heat energy. So you need to have constant external force, okay, so that the turbulence is maintained, okay. So this is one of the main feature, okay. So what have we discussed? So the features of turbulence or the symptoms of turbulence, it is diffusive, that is spreads out, okay. It is dissipative, okay, dissipative. It occurs at high Reynolds number, okay, and What was one more important thing, that is characterized by the swirling motions. Okay, so these are some of the important features, I would say, to characterize the turbulence. Okay, so once we know that, okay, so this is the turbulent flow, this is how we define the turbulent flow also. And when these characters are present, so okay, the flow is chaotic, it is unpredictable, and it is turbulent. So for example, if you have a flow in a pipe, if the flow is laminar, you know the velocity, this thing, right? What will happen if the velocity at this particular location is this much? I know how the velocity will become at the next location. But in turbulent flow, you cannot predict unless and until you solve the physics, okay? Or else in experiment, if you observe it, till then you will not be able to get the values of flow. Okay, you cannot predict. It is unpredictable in nature. That is also one of the feature. Okay, so these are some of the important features of turbulence, I would say. Then so once we discuss this turbulence, we see that it is like very chaotic kind of flow, and it cannot be described easily by our normal Navier-Stokes equations. But it is one of the most important flow without which this world might not have existed. Okay, so because what happens is that this turbulence kind of exists in each and every uh, uh, instant wherever you see, starting from our human body. Okay, so from the heart region, okay, you have a main artery which is known as aorta, which kind of supplies blood to all the other regions. Okay, so this blood flow in this aorta region is also turbulent in nature. Okay, uh, and that kind of efficiently circulates the blood into all the other arteries. In the other arteries, the blood sometimes behaves as a laminar flow. Okay, so if you see the carotid artery present in the neck region, or some other femoral arteries, or some other arteries, so there in many cases the flow is laminar, but in this particular aorta region, wherein the blood gets pumped first from the heart. Okay, so there the flow becomes turbulent. So starting from our human body itself, the flow is turbulent everywhere. Okay, so if you see like formation of rain droplets from water vapor in the clouds, that also happens due to turbulence. So in fact we get rain from turbulence only. Okay, so the water vapors present in the clouds, they have a turbulent mixing, and then it causes the formation of water droplets. So there also turbulence is needed. Okay, so like this, if we see the motion of water in surface of the ocean waves, many a times that is also turbulent, and it kind of enhances the mixing and transfer of energy, that is the transfer of heat energy. Okay, so this turbulence kind of enhances that, so that is why turbulence is necessary. So that was a natural phenomena. But if we see like a flow around an airfoil of an aircraft, okay, so during the takeoff of a flight, what happens is that there is an angle of attack due to which, okay, this might be a bit vertically aligned, the airfoil. So at these situations, what happens is that the flow separation kind of happens earlier, because the flow doesn't have the energy to hang on with this wall surface. So what happens is that because of this no flow region here, okay, a low pressure region is formed, because of which sufficient lift is not obtained by the this airfoil, due to which you can say that after certain angle of attack, the lift kind of decreases, which you might have studied also. And this particular point is called as the stall region. Okay, stall happens because you are not getting sufficient lift force because of this no flow region which is forming due to insufficient this thing, flow region. Okay, because of earlier flow separation. Okay, so what is done here is that in industrial application, while manufacturing these airfoils, people want to induce turbulence. Okay, so that is why they put something called as this vortex generators. Okay, on the airfoil. So mainly this will lead to formation of these eddies, which kind of are attached to the airfoil wall. Okay, and in this way we can prevent this no flow region, and then we can get sufficient lift. Okay, this stall can be prevented. Okay, so that is one practical application. There are many other applications also. Okay, which are made possible through the existence of turbulence. So this turbulence in a way is very practically important, although we cannot model it very accurately. Okay, but this is being harnessed very in a very wise way in industries. Okay, so after understanding these applications and getting an appreciation, so let us try to see some of the problems for today's tutorial session. Okay, so the first question is the behavior of small scale eddies in turbulent flow is best explained as. So the question asks mainly what is the feature of the small scale eddies. So as I said earlier, there are two types of swirling motions based on the length scale. They are mainly classified as large eddies or small scale eddies. Okay, based on the length scale, purely based on the length scale. Okay, so mainly these large scale eddies are non-isotropic in nature. That is, the fluid might be concentrated at say only at the core region or something like that, and the distribution might be different. So they are non-isotropic in nature, but they have one particular direction. Like when we saw in the experiment in this particular case, in the second case, we can see that the flow kind of goes in one particular direction only. So it has one particular direction, and they are not very directly dissipative. Okay, although I told that one of the feature of turbulence is dissipation, but these large scale eddies kind of take a very long time to dissipate into smaller eddies and all. Okay, so in general they are not dissipative in nature. Okay, but whereas if you see the small scale eddies, since they are concentrated in a very small length scale, you cannot have variation of fluid properties which is happening also. Okay, so they are isotropic. That is why they are isotropic, since they are concentrated on a smaller scale, and these might be non-directional now because they can go back and forth, which was observed in the third case. Okay, in mostly in the chaotic high turbulent flow region, they are non-directional, and since they are non-directional, what happens is that inherently they become dissipative in nature, because first of all they have less energy, and also they are non-directional, which kind of aids the dissipative nature. Okay, they can lose their energy very quickly. Okay, so you can see this in an experiment also. Whenever you try to stir the water in the tank, first of all you get very large eddies, and then they take some time to form some small eddies, but these small eddies kind of dissipate very early. Okay, then you have a very stagnant kind of flow which happens. Okay, so these are dissipative in nature. So the correct option, I would say, would be option number A and D. Okay, isotropic and dissipative in nature. Okay, that is the correct answer. Now coming to the second question, which is mainly based on turbulence intensity. Okay, turbulence intensity of a flow field is defined as like how do you define the turbulence intensity of the flow field? That is the question which is being asked. So, as I said earlier, we are mainly interested with the statistics of turbulence. We do not go on to calculate the actual fluctuating component, which I said earlier. We decompose the flow into mean component and then the fluctuating component. Okay, we are interested in the statistics of this fluctuating component, and the turbulent intensity is one statistical parameter. Okay, so that is a one statistical parameter. The way in which it is defined is as follows. So the turbulent intensity, it is defined as the RMS of the fluctuating component should be, it should be U dash RMS. That would be more appropriate, and then you have U mean or U reference. Okay, so that is the mean component of the flow. Okay, so in this way what you are trying to judge here is how much turbulence is there. See, if for example if you are getting a very high value of Ti, it is turbulence intensity, it what it indicates is this U dash RMS is very high, which means U dash magnitudes are higher, which means that the fluctuations are higher and turbulence is higher. So indirectly, this turbulence intensity kind of gives us how much turbulence is there in this flow. Okay, so that is the main idea behind calculating this turbulence intensity. I hope this is clear. So U dash RMS, you can define it as the RMS normal definition. Okay, you have three components in three-dimensional flow. Okay, so this question applies in general. So we'll take 3D flow. Okay, so it becomes then the RMS. What is it? It's square root of U dash square plus V dash square plus W dash square divided by 3. Okay, because you have three components. Okay, so then you have U reference as usual. So if you scan through the options, option number D should be the correct answer. Okay, but you have some other options also wherein the turbulent kinetic energy K is also present. So let us try to convert this equation in terms of turbulent kinetic energy. So turbulent kinetic energy is given as like K is equal to half of rho into U dash square. Okay, if you have one component, then if you have multiple component, half of rho into U dash square plus V dash square plus W dash square. Okay, so this U dash square plus V dash square plus W dash square which is there, you can write it as what can you write it as? You can write it as 2 into k, right, divided by rho. Okay, um, so that is the way in which you can write it. Okay, so if you are ignoring the density, that is the kinematic, you can say turbulent kinetic energy, so then you can just write it as 2k. Okay, if you are just ignoring the density here. Okay, so that would mean that this u dash square plus v dash square plus w dash square will become 2k, and 3 is as it is. Okay, so and then u reference is also as it is. So you can express the turbulent kinetic energy in this fashion also. So if you see the options, this k is actually in the numerator, it's not in the denominator, although it might appear so. Okay, so the option number A is also correct. Okay, because you can see that 2k by 3 raised to half, that is the square root divided by u reference, that is also correct option. So again, for this question also, option number A and D are both the correct answers. Okay, so if you see the question number 3, basically it is about the nature of this moments and what do they indicate. So again, this is a question which is related to the statistics of the turbulence. Okay, one thing which we saw is just now the turbulence intensity. We also calculate the moments of this fluctuating components. Okay, so in this question, the higher order moments of fluctuations provide more details regarding the distribution of fluctuations. Okay, so that is what the necessity for calculating the statistical parameters. Anyway, the third and fourth order moment are defined as follows. So they have given the definition of the third and fourth order moment. Okay, so the third order moment is nothing but the phi dash cube, which is being integrated over the time interval in which we are measuring. Okay, and similarly phi dash raised to 4, that is the fourth moment, you can say fourth order moment. Okay, so that is also calculated in a similar fashion. Okay, so the question asks the third and fourth order moments are linked to what. So let us try to see how this third and fourth order moment behave first of all. Then we can try to comment on what they indicate basically. So that is what is being asked in the question also. So phi dash cube, as it is given in this question itself, it can be calculated by taking the integral of um, uh, what do you say, phi dash. Okay, so if I say that this is one particular time interval, a very small time interval, if I take it as, and then I do the cube and then do the averaging. Okay, what is there in that time interval, I can see this, that this phi dash cube, which is the third momentum, third moment, it kind of behaves similar to this phi dash only, but it gets kind of amplified in nature. Okay, it gets amplified because we have phi dash cube. So for example, if you have 2 cube, it becomes 8, whereas if you have minus 2 cube, it becomes minus 8, right? So similarly the things get amplified in a, if I say, in a very simple fashion. Okay, so that is why this kind of nature is called as asymmetric or a skewed nature. because when you have small asymmetry it leads to a big asymmetry in this third moment. Okay, so that is why it is called a skewed profile, and it is anyway asymmetric in nature. So that is particularly the nature of this third moment. Okay, whereas if you see the fourth moment, okay, if you calculate 5 dash raised to 4, then you kind of have all in the positive range. Even the negative values of 5 dash, they kind of come into the positive scales. Okay, then you have only the amplified range. Okay, only the amplification you have. Okay, so you kind of get to know the intensity. Okay, in a crude sense. So this is known as peakedness of the turbulence. Okay, so this indicates the peakedness, or you can say kurtosis. Okay, so that is a technical term, more technical term. In general you can say how how much large is the turbulence or something like that. Okay, so that is mainly called as peakedness. So for this there are two options which are mainly correct here. So if you can see carefully, the third moment does not indicate kurtosis, so this is wrong. Okay, which is nothing but the peakedness. It does not indicate that. Okay, it indicates only the skewness. Second option is flatness. Definitely it does not indicate the flatness. It actually indicates the skewness, which is like the opposite sense. Okay, then the third option you have skewness for third moment, and kurtosis for the fourth moment, which is correct. Okay, and in the fourth option, you have asymmetry and peakedness, which are the synchronyms for this skewness and kurtosis. So both the options C and D are correct. Okay, so let us go to the next question. Examples of free turbulent flow are found in which of the following cases? Okay, so we have to identify where free turbulent flow are obtained. So before that, we have to understand what is free turbulent flow and what is confined turbulent flow or something, whatever, non-free turbulent flow, whatever it is. Okay, so basically, if we consider flow past an airfoil, so these eddies which are formed are kind of sticking to the wall region, and they are bounded in nature. So that is why they are not a class of free turbulent flow. Okay, so if you go to the second example, that is a mixing layer. Okay, here what happens is that it is a confined flow region which kind of expands freely. Okay, so then these eddies can expand freely in the space, and there is a free layer which is formed. Okay, so this kind of comes into the free turbulent flow example. Okay, and then if we have option number C, jet flow, it is also similar kind of flow, similar to the mixing layer. You have a free region wherein the fluid can expand after coming out of this orifice. Okay, so here also the flow expansion is quite free in nature. The boundary layer can grow freely. Okay, so that is why you have this particular kind of flow also as a example of free turbulent flow. Finally, you have pipe flow. Okay, so again here also, if you see, it is bounded by both the top wall and bottom wall. Okay, if you this is not actually top wall and bottom wall, in general wall. Okay, in channel it is top wall and bottom wall. Okay, pipe flow, it is bounded by the walls. Okay, the eddies. So that is why this is also again a bounded kind of flow. So the correct answers here are only the mixing layer and the jet, which is nothing but the B and C option. Okay. In question number 5, we have near to the wall. The nature of turbulence can best be explained by which of the following options? Okay. So basically, if we see the wall region, so for example, if we consider fluid flow above a flat plate, so basically we have this eddies which are formed, and they might be of different scales depending on the location wherein we are looking at. Okay, so initially what happens is that these small eddies might be formed. Okay, and later on the large eddies might be formed in this particular zone. Okay, so basically we have different length scales. Okay, so they are anisotropic in nature because we don't have same properties, the length scale, velocity scales across all the regions. So that is why they are highly anisotropic, they are not isotropic. Okay, so option number A is correct. And if you see the turbulence production, since the and you have the other option is low turbulence dissipation. Okay, so near the wall, actually what happens is that turbulence gets produced because of the wall effect. Okay, the uh, impingement of the fluid happens on the wall, and because of the skin friction which exists, especially in the case of hard walls or rough surfaces. Okay, turbulence gets produced and it is dissipated in the free near the free stream region. Okay, so this low turbulence dissipation occurs, it occurs in the far away from the wall region. Okay, so near the wall region turbulence production occurs. Okay, so that is the main difference between the two options. So it is anisotropic, the near wall region, and it is a region where turbulence production happens. Okay, so both A and B are correct options. If you see the question number 6, okay, so the terms, these terms belong to which of the following equations? Okay, so as I told, what we do is that we kind of decompose the flow into the mean component and say the fluctuating component. So in general, it write as phi is equal to some mean component phi plus phi dash. Okay, so this we substitute in the Navier-Stokes equation. Okay, so when we substitute, for example, in the y momentum equation, we have dou v, we substituted dou v plus v dash mean component. Okay, divided by dou t plus the advection terms similar to that. Okay, minus dou of capital P plus P dash. Okay, divided by dou y, okay, plus the viscous terms. Okay, so what happens is that this dou v dash by dou t anyway goes to 0. Okay, you are left out with this advective terms and the viscous terms. Okay, so in this also, if we see what remains when you do the derivation is this Reynolds stress term like u dash v dash, okay, or u dash square. Okay, these kind of terms remain out. Okay, so if you see this equation, mainly we have v dash square upon dou y. Okay, so if you see through the weekly contents also, this v dash square by dou y, it mainly comes in the y momentum, which you can predict also. Okay, because this Reynolds stress terms, like they come as conjugate terms here. So in the x momentum equation you have u dash square, in the y momentum equation you have v dash square, in the z momentum direction, z momentum equation you have w dash square. Okay, so this kind of corresponds to the this particular equation which they have given here. It mainly corresponds to the momentum equation in y direction. Okay, and it is the momentum equation for the mean component. Okay, since dv by dt is there here, so it is nothing but the time averaged momentum equation for mean velocity. It is not the turbulent kinetic energy equation. In turbulent kinetic energy equation, we have the equation for K. Okay, that is a different equation where these terms do not come into picture. It is not an equation for epsilon also. Usually you see this in K epsilon model. Transport equation for density, no. It is the continuity equation wherein we don't get to see these particular terms. Okay, uh, so the correct option here is option number D. Okay, let us go to the last question before going into the marker and cell algorithm for Navier-Stokes equation. Okay, according to Prandtl's mixing length theory, in a flow where only significant mean velocity gradient is dou u by dou y, so we don't have like dou v by dou x and all those things, we have only dou u by dou y, the Reynolds stress is proportional to which of the following terms? Okay, so the Reynolds stress is mainly given but nothing but the wall shear stress, which you calculate as usual, turbulent viscosity, okay, into the gradient of the x velocity, mu t into dou u by dou y. Okay, so this mu t you can write it as rho into kinematic viscosity, just some simple alterations. Okay, so this turbulent viscosity, okay, it can be written using the Prandtl's mixing length theory as the mixing length square into this magnitude of velocity gradient. Okay, so this kinematic viscosity, that has been replaced here by this term. Okay, so I hope that it is understood here. Okay, so mainly finally we have if we take the proportionality, then we can ignore the rho. Okay, so then we have lm square, mixing length square, and to the magnitude of this velocity gradient, and this normal velocity gradient comes in the definition of the wall shear stress only. Okay, so if you see the options in particular, option number B should be the correct answer. Okay, so these were some of the questions which I wanted to discuss. Okay, mainly you need to kind of understand the main modeling approaches, although it is not required that you kind of go and do the modeling. Okay, so you can use some open source software or even some commercial softwares. Okay, so mainly to understand. Okay, I would suggest to use some open source software to understand, because there the understanding will happen in a much more better fashion. Okay, if you want to really work on turbulence. Okay, so those are some of the things which I wanted to mainly suggest here. So this is about the today's content. Okay, so let us try to see one of the important algorithm through which you can solve the Navier-Stokes equation. Okay, this is mainly called as a marker and cell algorithm, as I told earlier. So in short, it's called as MAC algorithm. Okay, so previously we had seen that we can use the vorticity stream function to solve the Navier-Stokes equation, but it was mainly limited to two-dimensional flows. Okay, but this marker and cell formulation, which is based on finite difference method, okay, this can be applied for 3D flows also. And this is just an extension of SOLA algorithm, which we had mainly seen in the previous weekly contents also. Okay, so it is very similar to your vorticity stream function approach only. First of all, you kind of write down the governing equations in terms of this conservative format. Okay, then you take the gradient, the x gradient of x momentum equation, y gradient of y momentum equation, and then just add them together. Okay, but here you don't then go on to express them in terms of vorticity and stream function, so that we don't do here. Okay, we keep the pressure as it is. We don't try to dismiss or eliminate the pressure term. Okay, in this particular formulation. So when you just add them, so basically LHS and RHS are formulated separately, and then finally you kind of come up with a pressure Poisson equation. So through this you can separately calculate the pressure also. So that is how we come up with an explicit equation for pressure. In this, D is nothing but the our continuity equation terms. It is the mass continuity. Okay, so it is basically dou u by dou x plus dou v by dou y in two dimensions. Okay, so that we do not make it zero. Okay, because we are doing it in a computational setup, and so ideally it will not be zero, although it should be zero. But what we do is that we try to make it zero. So that is the main intention here. So we kind of have momentum equations, and then we also got a pressure Poisson equation. So that is what we all need. Okay, so so as discussed in the previous classes, we are using staggered grid. Okay, so what we do is that if I come to just to the algorithm directly. Okay, so first we kind of apply the boundary conditions as usual, and then we compute the this dij, which is nothing but the continuity dou u by dou x plus dou v by dou y on all the sets. Okay, it will not be zero in the internal grid points. In the next time step we intend to make it zero. That is why in the whenever we kind of calculate dou d by dou t, which comes here, like dou d by dou t comes in this pressure Poisson equation. Phi is nothing but pressure. Okay, so dou d by dou t, when we calculate, we have d at n plus 1 time step, so this we make it to be 0. Okay, so that is the main thing which is done here. D at n plus 1 is made 0. D at I of j we calculate using our whatever velocity values which we have. Okay, so that is what is being done, and through that we kind of first evaluate the pressure. Okay, that is the phi. We already know the velocities at the previous time steps. We have calculated the d value, through which we evaluate the pressure. Okay, so that is the first thing which is done. After evaluating the phi using the values of phi, we solve the momentum equation to kind of get the values of velocities. Okay, so that is the main algorithm which is used. Okay, so briefly I'll go through the code also once. Okay, so you can see the code which I'll be attaching with this PPT anyways. You can go through it later on also. So first, what is being done is that we enter the time stepping after initializing the variables. Okay, so that is very important, and we are again solving the lid driven cavity problem which we had dealt with in the week number 9 also. Okay, so in week number 9 also, whatever problem was considered, same problem is being considered here. Okay, so we initialize all the flow variables first. That is the first step. Okay, so then we come into the time stepping. Okay, wherein first, as I told earlier, we first calculate the value of d. Okay, nothing but du by dx plus dv by dy in two dimensions. Okay, and then we can also apply the boundary conditions for d. Okay, then we kind of calculate the pressure by solving the pressure Poisson equations. We just calculate the RHS, which we call as R. So that is what is called as computation of R. R means RHS for this pressure Poisson equation. Okay, so that you can calculate very easily. Okay, once we calculate the RHS, we can solve the pressure Poisson equation iteratively within a particular time step to calculate this pressure, which is called as phi here. Okay, so once you are calculating the phi, then you can go to calculate u nu and similarly v nu. That is by solving the momentum equations using the value of phi x, that is d phi by dx for x momentum and d phi by dy for y momentum. Okay, so that is the main technique which is used here. So and then mainly you calculate the difference between the two time steps for velocities, and if they are going below certain value, here I have set it to 10 raised to minus 5. Okay, so below, if they are going, we say that the flow has reached the steady state, and then we end the computations. Okay, so that is the main kind of algorithm. Anyway, I will be attaching this code with the PPT also. You can go through it and you can try to run it and just check. Okay, so mainly I have already run the code. Okay, and we have the results also data file with us. Okay, when we run the code, we kind of, when we reach the steady state, we write the results into the data file. Okay, like how to run the code also I have explained it in the week 9 contents. You can go through the week 9 video lecture and see how to run this code. Okay, especially if you are using Windows operating system. In Linux, it is very easy actually. All the things comes preloaded. Okay, so there it's actually pretty easier. But in Windows also, I have told how to kind of run this code. Okay, yeah. So I'm just trying to visualize the flow field using this ParaView software, which is an open source software. Okay, so this is basically the domain. So if I, like, for example, write the data access grid. Okay, you can see that the length and width are zero point 0.1 and zero point 0.1. Okay, and then you can see the grid also. I have used a very coarse grid here, 40 cross 40. Okay, you can define the grid and all. Okay, in this code you can do that very easily. And then you have the values for velocity, which you can try to visualize using different color schemes also. Okay, so you can take a velocity profile along one particular direction and then compare it with the literature to see whether this code is correct or not. Okay, so that you can try yourself. Okay, okay. So thank you for your attention. Okay, so if you have any queries, you can write down in the comment box. Okay, especially regarding this code and all something. Okay.